Hello everyone, I'm a training professor at Huawei. In this class, we will study RAID technology together. The important purpose of the development of RAID technology is data protection and performance improvement. After completing this course, you will be able to list common RAID types, list different levels of data protection provided by different RAID types, understand the technical principles of RAID 2.0, and understand the algorithms and RAID depot of dynamic RAID. First is the first module, Traditional RAID Technology. RAID is a term defined in a paper published by the University of California, Berkeley in 1988. The purpose of Berkeley University's research is to reflect the rapid performance of the CPU at that time. The performance of the CPU grows by about 30% to 50% each year, while the hard disk can only grow by 7%. Therefore, the research team hopes to find a new technology that can immediately improve performance in the short term to balance the computing power of the computer. The main functions of RAID technology are to combine multiple hard disk groups into a logical hard disk group to provide larger storage capacity, divide our data into data blocks, read and write in parallel to multiple hard disks, and improve the access speed of hard disks. By providing mirroring or parity check to provide a fault tolerance, RAID function can be implemented in storage devices in two ways, hardware RAID and software RAID. Hardware RAID uses a dedicated RAID adapter, hard disk controller, or storage processor. The RAID controller has its own processor, I/O processing chip, and memory, which is used to improve resource utilization and data transfer speed. Hardware RAID is usually used in servers. Software RAID does not have its own processor or I/O chip and is completely dependent on the host's CPU. Therefore, a slow CPU cannot meet the requirements of RAID implementation. Software RAID is usually used on enterprise storage devices. For the data organization of RAID, the hard disk space is first divided into multiple stripes of a set size, and data is written in accordance with the size of the stripes to divide data modules. A stripe is a single or multiple consecutive sectors in a hard disk and is an element that makes up striping. Striping is a stripe with the same position or the same number in multiple hard disk drives in the same hard disk array. The width of striping refers to the number of disks used when a hard disk group is striped. Like in this example, it is composed of 3 members, and its stripe width is 3. The depth of striping refers to the capacity size of a stripe. RAID technology usually has 2 different ways to protect data. One way is to save a copy of the data on another redundant hard disk to improve reliability and can improve read performance. The second is to use GeoCheck algorithm. GeoCheck code is additional information calculated using user data. For RAID types that use GeoCheck, it means an additional check hard disk. GeoCheck uses the XOR algorithm, and its symbol is shown in the figure. With the development of array technology, many different types of RAID have been produced, but now only a few types of RAID are still in use. Among all RAID levels, RAID 0, also known as striped RAID, has the highest storage performance. RAID 0 uses striping technology to distribute data storage across all hard disks in the RAID group. A RAID 0 contains at least 2 member disks. The RAID 0 group divides the data into data blocks of different sizes and writes them in parallel to different hard disks. As shown in the figure, the first 2 data blocks are written to stripe 0, where the first data block is written to stripe 1 of hard disk 1, and so on. In this way, the I/O load is balanced across all hard disks in the RAID, and since the speed on the data bus is much greater than the read and write speed of the disk, the hard disks on the RAID group can be considered to be reading and writing at the same time. RAID 0 is like providing a single large capacity disk with very fast I/O characteristics. Before using RAID 0, a technology similar to RAID 0 was called JBOD. A JBOD is a group of hard disks combined into a virtual large hard disk. The data blocks of a JBOD are not written in parallel to different hard disks at the same time. In JBOD, only when the storage space of the first hard disk is used up will the second hard disk be used. Therefore, the total available capacity of JBOD is the sum of the capacities of all hard disks. But the performance is only the performance of a single hard disk. RAID 1 uses 2 identical hard disk systems and sets up mirroring. When data is written to the hard disk, a copy of the data is stored on the mirror disk at the same time. When the original hard disk fails, the mirror disk takes over the service from the original hard disk to ensure the continuity of the service. The mirror disk serves as a backup, providing high data reliability. The storage data volume of a RAID 1 group is only the capacity of a single hard disk, and the other hard disk saves the copy of the data, equivalent to every 1 GB of data storage. It takes up 2 GB of data space. Therefore, the space utilization rate of a RAID 1 composed of 2 hard disks is only 50%. RAID 0 uses striping technology to write different data in parallel to the hard disk, while RAID 1 writes the same data to each hard disk at the same time. The data in all member hard disks is the same. As shown in the figure above, data blocks D0, D1, D2, etc. are waiting to be written to the hard disk. D0 and its copy are written to 2 hard disks at the same time, and other data blocks are written to the RAID 1 hard disk group in the same way. Therefore, generally speaking, the write performance of a RAID 1 is the write performance of a single hard disk. RAID 1 reads data by reading the data disk and mirror disk at the same time to improve read performance. If one of the hard drives fails, data can be read from the other hard drive, so the read performance of the RAID 1 system is equal to the sum of the performance of the 2 hard drives. RAID 3 is similar to RAID 0. The difference is that RAID 3 has a dedicated parity striping. In RAID 3, a dedicated hard drive called a parity disk is used to save the parity values of the data in the corresponding stripes on other hard drives. If incorrect data is detected or a hard drive fails, we can use parity data to recover the data on the data hard drive. However, when new data is written, regardless of which hard drive it is written to, RAID 3 needs to recalculate and rewrite the parity information. Therefore, when an application needs a large amount of writing, the parity disk of RAID 3 has a large workload, so it is often the most likely to fail hard drive in RAID 3. RAID 5 is an improved version of RAID 3 using striping and calculating parity information. In RAID 5, data is written to the hard drive group in the form of striping. The parity information of different stripes in RAID 5 is not stored separately in a fixed parity disk, but is distributed and stored according to certain rules. The write performance of RAID 5 depends on the amount of data written and the number of hard drives in the RAID 5 group. The data protection of the RAID group discussed earlier is considering the scenario of a single hard drive failure, and the capacity of the hard drive has increased a lot now. A RAID 5 formed by many large capacity hard drives may take several days to rebuild a failed hard drive, not a few hours. During the rebuilding process, the system is in a degraded state. In this case, any additional hard drive failure will cause the hard drive group to fail and data loss. This is why some organizations and units need a dual redundancy system. In other words, a RAID group should allow all data to be accessible when 2 hard drives fail. There are different ways to implement this type of dual redundancy data protection. The first one requires multiple mirroring. Multiple mirroring means storing multiple copies of the data disk on multiple hard drives at the same time, which means a lot of overhead. The second method is RAID 6 level hard disk array. The RAID 6 group provides protection for 2 hard drive failures, and these hard drives can even fail at the same time. The essence of RAID 6 is an improved RAID 5, which also has striping and distributed parity. The additional parity information requires the storage space of 2 disks, so we generally regard RAID 6 as an N+2 type of RAID. Currently, there is no unified standard for RAID 6, and different companies implement RAID 6 in different ways. The following are 2 main implementation methods: RAID P+Q and RAID DP. When RAID 6 uses P+Q parity, P and Q are 2 independent parity values, and they use different algorithms. User data and parity data are distributed on all hard drives in the same stripe. As shown in the figure, P1 is obtained by XOR operation on stripe 0, where D0, D1, D2 are located. P2 is achieved by XOR operation on stripe 1, where D3, D4, D5 are located. Q1 is a mathematical transformation of stripe 0, where D0, D1, D2 are located, implemented by XOR operation. We use an asterisk to represent this mathematical transformation. If a stripe in a hard drive fails, only the P parity value is needed to recover the data on the failed hard drive. If two hard drives fail at the same time in a stripe, different scenarios have different processing methods, which is equivalent to solving the related equations of PQ. Another algorithm is RAID 6's DP algorithm. RAID 6 DP also has two independent parity modules. The first parity information is the same as the first parity value of RAID 6P+Q. The second one is different from RAID 6P+Q and uses a diagonal XOR operation to obtain the row diagonal parity data block. As it's shown in the figure, P0 is obtained by XOR operation of D0, D1, D2, D3. P1 is obtained by XOR operation of D4, D5, D6, D7. DP0 is obtained by XOR operation of stripe D0 of hard drive 1, stripe D5 of hard drive 2, stripe D10 of hard drive 3, and stripe D15 of hard drive 4. DP1 is obtained by XOR operation of stripe D1 of hard drive 2, stripe D6 of hard drive 3, stripe D11 of hard drive 4, and stripe 3 of the first parity disk P3. In this way, a RAID 6 array can tolerate the failure of two hard drives. As shown above, if hard drives 1 and 2 fail, all the data above will be lost. But the data and parity information on other hard drives are valid, so the information of the failed disk can be recovered based on the diagonal check and horizontal check. The performance of a RAID 6 group is relatively slow whether the algorithm is DP or P+Q. So RAID 6 is suitable for two scenarios. The data is very important and needs to be online and in use for as long as possible, or the hard drive capacity used is very large, usually exceeding 2 terabytes. Let's look at RAID 10. For most enterprise customers, RAID 0 is not an operable choice, and RAID 1 is limited by hard drive capacity utilization. RAID 10 combines RAID 1 and RAID 0 to provide the best solution. The number of hard drives in RAID 10 is always even, half for user data writing and the other half for saving mirror copies of user data with mirroring based on striping. In the figure, physical hard drives 1 and 2 form a RAID 1, physical hard drives 3 and 4 form another RAID 1, and these two RAID 1 subgroups form RAID 0. When RAID 10 writes data, it writes data in parallel between subgroups, and data within subgroups is written in a mirrored manner. As shown in the figure, D0 will be written to physical hard disk 1 and the replica will be written to physical hard disk 2 when hard disks in different RAID 1 groups fail. Such as hard disks 2 and 4, the access of the RAID 10 group is not affected. This is because the other two hard disks, 3 and 1, have complete replicas of the failed disks 2 and 4. However, if the hard disks of the same RAID subgroup, such as hard disks 1 and 2, fail at the same time, the data will not be accessible. Theoretically, RAID 10 can tolerate the failure of half of the total physical hard disks. However, in the worst-case scenario, when two hard disks in the same subgroup fail, RAID 10 may also experience data loss. RAID 10 is usually used to protect against the failure of a single hard disk. RAID 50 is a combination of RAID 0 and RAID 5 with two subgroups configured as RAID 5. These two subgroups then form a RAID 0. Each RAID 5 subgroup is completely independent of the other. RAID 50 requires at least 6 hard disks because a RAID 5 group requires at least 3 hard disks. As shown in the figure, physical hard disks 123 form a RAID 5, physical hard disks 456 form another RAID 5 group, and a RAID 0 is formed between the two RAID 5 subgroups. In RAID 50, RAID can simultaneously accept the concurrent failure of multiple hard disks. That's the content of this lesson. In this lesson, we learned about traditional RAID technology, listed common RAID types, and different types of data protection, etc. In the next lesson, we will learn about Huawei's RAID 2.0 Plus related technology. See you in the next lesson.